to be like that. That will make them much easier to debug and to maintain, and so it's really important. So it's important to know exactly what it is. So I'm going to try to give a real precise definition so you know exactly what is declarative programming. Okay? But the first part of the course will be on laziness. Before that, I want just a few seconds of silence for the Ukrainians who are fighting for us and for them. Okay. These slides are improved slides from last week, more complete. So if you took the old version, I suggest you take the new version. And I've added a whole bunch of stuff. Today, I want to, first 2 minutes, refresh your memory on laziness. Okay, when I have a lazy add, when I execute this, it creates a lazy suspension. What is a lazy suspension? It's just a thread with a wait needed in there. Notice the R is the result. It waits until the result is needed. What does that mean? It means another thread uses the value of the result. If I do an addition that needs the result, then the wait needed will continue. So wait needed is a really special kind of data flow operation, and it's implemented in the system. So you can try it out and use it, but the lazy functions will use it implicitly. Okay, so that's how it works. This is what we saw last week. I'm not going to go over too much. Let me go over just one thing. Remember the Hammock problem where we had to find a list of numbers. These numbers have lots of gaps, 2 to the A, 3 to the B, 5 to the C, and we want to have them in sequence, with all of the ones in sequence. So how do we do that? That's really easy to program when you use lazy valuation. We take 3 streams, 2 times H, 3 times H, 5 times H, and we merge them together. And this is an infinite loop. But that's okay in laziness. Infinite loops are very usual and very good in lazy programs. Okay? But I want to show you I want you to really understand what's going on. Now, you saw the definition of lazy add seems to be very simple. But usually when you have a lazy program, you have lots of lazy functions connected to each other. One of them is using the result of the other one, so there's a long chain, and I want you to understand a little how that works, just to refresh your memory. So here's the merge. This takes 2 streams, S1 and S2, which are both ordered, and merges them together. So the result is an ordered stream with all the elements of the input streams. Okay, this is a lazy function. This one will only execute if I need the result of the stream. And notice inside this function there's a case. This case statement needs S1 and S2. So you can see there's kind of a chaining. If I need the result of the merge, then there will be a chain effect, and it will also need S1 and S2, and it will go back like that. Okay, so let me show you a little bit how that works. Here is what happens when you execute the Hammock program. You create 5 lazy suspensions, threads waiting on wait needed. The merge T2 M2 is waiting to create M1, okay, and merge T3 T5 is waiting to create M2, and so on. Now I want to show you a little bit more how that executes, because we're going to use that, and I want to show you in a few minutes a really interesting trick, a really magic thing. But to understand that magic thing, you have to get this. You have to understand what's going on here. Okay? Now let's say I want the second value of H. I know the first one, which is 1. So in order to get the second value, I need to do M1 dot 1. That dot operation needs M1. Okay? The dot is a record selection, and M1 will be a list with 2 arguments, but it's still unbound here. So when I do dot M1.1, it needs M1, and a wait needed on M1 will continue. So the merge T2 M2 will activate. That means it will start executing the body. Okay? Now, just to show you more in detail, so I do browse M1.1. This shows the second element. This will activate. Now this dot operation sees an unbound variable, so the dot operation will just wait. Okay? It just sits there and waits. But while it's waiting, another thread activates the merge M2, T2 M2, and that will execute the body of the merge. Remember, a merge will merge 2 streams, so the body has a case. Here it's with T2 and M2, so I need the first element of T2 and I need the first element of M2. T2 and M2 also have lazy suspensions attached to them. So I make them in red and green to make it easy to understand. When I do case T2 of H1 bar T2 prime, this will cause T2 to be needed, and therefore times H2, which has a wait needed, which is attached to that, will activate, will start running, and M2 needs, so here the case M2 of H2 M2 bar will need M2, and this will activate the one that's waiting on M2. So the red and the green suspensions will both activate. So you see there's a chain, huh? I start with M1.1. This activates the merge here. When I execute the body of that one, the case will activate 2 more lazy suspensions. So the case statement needs the first elements of T2 and M2. This will activate the red one and the green one. And what does the case do? Well, the case will just wait. Okay, the case just sits there in its own thread and waits until T2 and M2 are bound. It just sits there. And in the meantime, times H2 and merge T3, T5 are running in their own threads. So you see, there's a lot of threads waiting. Huh? This one is waiting, and then this runs, and then this case waits, and then these 2 run. So at some point you have lots of threads waiting, like in a chain. Okay? Okay, so explain a little more. So the red one and the green one are both running. So the body of times H2 is executed. This will bind T2, the result to 2 bar T2 prime. That means T2 now has a value. So the case statement is very happy. The case statement here in the previous slide, the T2 now has a value. So the case statement is very happy. Of course, there's still the M2. It also does a recursive call, this times T2 prime, which creates a new lazy suspension. So you see what happens. When you activate a lazy suspension, it creates a piece of the value, but it also creates another lazy suspension for later, okay? And the green one also is activated, merge T3, T5. I execute the body of that. That's also a merge. It has its own case statement, and that will cause these 2 more times to be activated. And that goes on. I'm not going to show all the details, but eventually M2 is bound to 3 bar M2 prime, and a new lazy suspension is created on M2 prime. So again, it binds and creates a new lazy suspension. And now the case statement is happy because both T2 and M2 have values, 2 and 3. And this case, which was waiting all the time, now sees those 2 values and can continue. So you see, it's a very simple kind of synchronization. The case needs something. This causes the lazy suspension to wake up. It does stuff. Eventually it binds it. And the case that was waiting will continue, okay? And then it keeps going, and so on. And that case then executes, and it actually does the merge, and it returns 2 bar M1 prime, and creates again a new lazy suspension. So the dot M1.1 will be bound to this. So M2 bar M1 prime, so that 2 will be displayed, and a new lazy suspension is created on M1 prime. So what happens when you execute M1.1? A lot of things happen, okay? All these lazy suspensions, 5 of them, are all activated. They all run. They all bind variables, and this causes the result. But they all create a new one. So there's 5 new lazy suspensions. So 5 threads wake up, they run, and then they create new threads that are sleeping again, new lazy suspensions. So this simple M1.1 does a lot of things, okay? You have to understand that. It seems very simple, but there's a lot of connections between the different mechanisms, okay? So that's something you have to keep in mind. And there's a chaining effect, okay? If I activate a lazy suspension, it executes the body, but that body might need more things. So those more things will also be activated, and so on. And that can go very, very long, as we will see when I show you the lazy quicksort. This is just warm up, okay, to the example I want to show a little bit later. Okay, so you see how it works, eh? And all of that is one single new operation, wait needed. So I'm not doing a real complicated new language. I only add one new operation, and you can see this can cause a lot of different kinds of mechanism to run, okay? So you see a very nice, complicated, orchestrated computation can be done with only very simple thing added. This is important. When you build applications later, you should do the same thing. If you want to make a big application, try to add only one thing, or just a few things to do everything, okay? It's by far the best way. Okay, I made also a picture here. If you follow the arrows, so this is a new slide. M1.1 on the top left, it's activated. I see merge T2, M2. This causes the body to execute. T2, M2 are in a case, so they both activate. Here the T2, bind T2, here, and this binds M2. And this merge T3, T5 again causes the body to execute. So T3 causes this one to execute and bind T3, T5 does that. All of that is done when I do M1.1. And the M1.1 is not doing very much. It just waits. So I try to do the dot operation. I notice that M1 is unbound variable, and I wait. That's all the dot is doing. It's not doing anymore. It's just waiting. But there's, on the other side of the system, a wait needed that notices that, and it does all the work. And so the M1, the dot which is waiting, it just waits, and eventually, magically, M1 gets bound. Ta-da, and it can run. So the dot is actually not doing anything here, okay? Everything is done behind the scenes. From the viewpoint of the dot, I just try to do a dot operation, and I wait, and eventually, magically, the value appears. That's all the dot operation is doing here, okay? All the work is done in another part of the system. Okay, so that's kind of neat, isn't it? So this is the mechanism of lazy evaluation. Now, so this is stuff we saw last week. We saw also the bounded buffer, but I didn't get a chance to finish it. I want to show you the execution of this thing, of this beast, because this is also a nice example of where lazy and concurrency are coming together. Okay, so the bounded buffer is a magic component that you can stick inside any pipeline. So here I have a pipeline. I can just stick the bounded buffer in there, and I don't have to change the code of the producer and the consumer. Okay, and the performance is improved. So that's nice, huh? It's very modular. I have a system. It's doing badly. I stick in a new thing without changing any of the code, and it does better. That's good, huh? So the bounded buffer is a nice thing, and it's used a lot. And it can be written in lazy deterministic data flow. So it's a completely declarative thing, bounded buffer. That's not something that many people understand. Okay? What I'm telling you in this course is kind of the leading edge of declarative programming. Yeah? This bounded buffer is completely declarative. If you ask people to do that, they would probably tell you it's impossible, but it's not. Huh? So we will write the bounded buffer, and I did it in 4 steps. I will just go very briefly, but then I want to show you the execution, how it works. Okay? So it's a procedure with 3 arguments: input stream S1, output stream S2, and n, which is the size. How many elements? It's a bounded buffer. Of course, we have to be careful it doesn't grow forever, so it has a maximum size, and that's n. Okay. And we do it in 4 steps. So the first step, all the input elements are just going to the output. Okay. We have lazy, so maybe the input elements come in early or later or whatever, but the bounded buffer is not creating any new elements. Huh? It's just passing the input to the output. So the basic loop is just a no-oppa, which this loop which is just passing input S1 to the output. S2 equals loop S1. So that's the basic thing. But of course we use laziness to make this thing work, work in a special way. Okay? The bounded buffer, it looks like a consumer from the viewpoint of the producer. Huh? So the producer thinks it's just sending elements. So the first thing the bounded buffer, when it starts up, is it asks for n elements. Okay, that's reasonable, because the producer, the bounded buffer, tries to stay always full. Okay, it tries to stay full, and when it's full, then it stops asking, and it becomes it's going from eager to lazy. Yeah. So it's asking eager elements, but once it's full, it stops and it becomes lazy again. So here it asks, so list.drop is just a list function that traverses a list and removes the first n elements. Okay. So that's the startup. And then it has to stay full. The bounded buffer is always trying to stay full. When the consumer takes an element out, then there's one less element in there. So it asks the producer for another element then. It's always trying to stay full, the bounded buffer. And how do we do that? Well, we add an extra argument to the loop. Whenever the consumer asks an element, then this lazy function will execute. The body will run, so this will be activated. Whenever this body runs, that means the consumer has asked for an element. Okay? So this run is triggered by the consumer. Okay? And what we do here is end is actually n elements farther down in the list. So we call it with n.2, which goes one step farther. And that's a message to the producer. Okay, the dot operation needs end. And so the producer, which is lazy, activates again and tries to make this element. Okay? So this makes sure that the buffer always stays full. Okay? And then there's a final step, because n.2 is a blocking operation, and the same for list.drop. The end will wait, n.2 will wait until the producer makes the element. But we don't want to wait. That's separate, huh? The producers, we don't want the whole buffer to wait for that. So how do we solve that? It's very magic. In declarative programming, you can add threads whenever you want. Adding a thread will never make a bug. Okay? In a declarative concurrent model, threads are easy things. Most people are scared of threads. Huh? Threads in Java are very scary things because you introduce many bugs. But threads in declarative programming are not scary. They are your friends. You can add them whenever you need them. And you don't have to worry. You will never add a bug by adding a thread. And so if I don't want this n.2 to block, it's very easy to fix that. I just stick it in its own thread. And the thread, that thread will wait, but the bounded buffer will not wait. And so this list.drop also has to be put in its own thread. So these two operations, so the startup here, the startup thing here, and the staying full thing have to be put in their own threads. Otherwise, the buffer is going to be waiting until the producer generates the elements. But we don't want the buffer to wait, so we just put them in their own threads. And this will not add any bugs. It will just make the buffer go forward. It will allow it to go forward. That's it. Okay? So you see, declarative programming is actually very easy. Huh? Concurrency is very easy. So this is the full bounded buffer now. That's it. That's the whole code. Okay? And it's completely right. Now I want to show the execution of this before going on to the next example. So the execution, I would have a producer, prod, and consumer cons. And I stick the bounded buffer in the middle there. Okay? But I want to show you the code for that. Okay. I think I will have to restart this guy if it eventually restarts. There it is. Thank you. Docker images take a long time to start. You know why? Huh? Because they're very big. And this one is like 1.5 gigabytes because they're like complete computers. Okay. So it takes a little bit to start. So here it is. So let me now look at the bounded buffer. First, let me do a producer consumer here. Okay. So this is a simple producer consumer, lazy producer consumer. Okay. Let me just run that now. So I do that. Do this. Notice this is lazy, so you see nothing here. If I want this thing to run, I have to ask very politely. I have to need something. So if I want the second element, for example, I do s2.2.1. Okay. It will now do it. Notice there's a delay of 1,000 there, so it takes a little while, but you see it produces the elements. Okay. And now let me show you the bounded buffer on this thing. So here is the bounded buffer. Paste. Okay, and now I want to, well, let me compile it first. Oops. Okay, the scrolling is not so great here. Let's see. There. Now I will take this one and I'll stick the bounded buffer in there. That, that's right here. Okay. Okay, and the bounded buffer goes in the middle.
S1, S2. Let me make a small one of size 3 to make it easy to see. This then becomes S2. This is S3. Let me get rid of this one now. Okay. Notice I have 3 things now. S1, which is the input of the bounded buffer, is coming from the producer. S2, which is the output of the bounded buffer. And S3, which is the output of the consumer. And the only reason I have S3 is so that I can ask for things. Huh? So it looks like this. Huh? S1, S2, S3. So the bound buffer is in there. So that's how it looks. Okay, I did compile it, I think. Yeah, let me try it now. So is my code right? I think it should be okay. Yeah? So now I'm running it, but I'm not asking for anything yet. Notice I did not ask, but already the producer has made has gotten 3 elements. That's the bounded buffer in action. The bounded buffer has already asked the producer to fill up. Okay. Well, let me ask for one more element. So this will be S3 dot 1. So I'm now asking for the first element from the consumer. But I know the first element, it's equal to 1. Huh? So the consumer will give this element instantly because it's already in the bounded buffer. It doesn't have to wait for 1 second. Okay? So when I do that command, the 1 will appear instantly. I don't have to wait for a second. But then another thing will happen. The bounded buffer now has only 2 elements. So it's going to ask the producer to fill up again. Okay? So you see the 1 appears right away, and 1 second later there's a 4. So you see what happens? When the consumer can immediately take elements out of the bounded buffer until it's empty. It can't do that forever, but if 1 element is easy, takes it out. And the bounded buffer always tries to stay full. Okay? So I do browse S3.2.1. Now if I now ask for the second element, this element I will see it immediately because the 2 is already there. And then the bounded buffer will ask for another element. No, it's 3, sorry. It's 3 because it's the output of the consumer. But it will, because the output of the consumer is the sum of the 2 previous elements. Okay, so it shows the 3, but notice that the input is going to 5 now. So the buffer always tries to stay full. Okay, you see how it works? So that's the magic of a bounded buffer, and that's completely done using lazy deterministic data flow. Combination of laziness and concurrency. The concurrency here is easy. I'm only using it to avoid waiting. Because the buffer actually, the producer can get ahead of the consumer. There's kind of a slack between the producer and the consumer. They're not really synchronized. The producer can get a little bit ahead because of the bounded buffer. And so that means because they're not synchronized, they have to be kind of little independent. Okay? So that's one way of seeing why you need concurrency. If you want 2 things to be kind of independent and not synchronized, you need some kind of concurrency. Okay? So that's the bounded buffer. Okay? So I'm not sure if the code is in the Moodle, but I will put it, it will be on the Moodle today. And you should try running it and playing around with this. Okay? So this is something you have to understand. Because this is probably the most powerful form of declarative concurrent thing. This is the most that we will see. It's the most powerful form I know of. Maybe in the future people will invent more powerful ones. Okay? But it's very strong. You can write a bounded buffer completely declaratively.
And you have to think declaratively now. And it's a totally different way of thinking than concurrent programming in Java. Because in this model, threads are good guys. They are cheap. They will not introduce bugs. In Java, threads are expensive. And if you don't think carefully, they will introduce lots of bugs because of the shared state. So threads in Java are considered nasty buggers. But in declarative concurrency, threads are your friends. Okay? Okay, so that's one thing. Now I want to show you a really neat example, which is lazy quicksort. This is showing really the power of laziness. Laziness can do really smart things sometimes, okay? When it makes things incremental. Okay, so let me explain a little bit. So I'm going to show you a sort algorithm. Sorry, I should probably show it as a slide. It's nicer. So lazy evaluation, we saw it can make algorithms incremental. So it's only creating things when we need it piece by piece. Okay, now I'm going to show you what happens when we use laziness on quicksort. So quicksort is a sorting algorithm, famous sorting algorithm that you probably saw. So do you know, who knows quicksort? You know quicksort? Some people know quicksort, okay. So we're going to use quicksort and turn it into something lazy, and then we see what happens. And actually, it's kind of a magic thing. So the standard quicksort, if I want to sort n elements, it has a time complexity of n log n, which is very typical for a sorting algorithm to sort n elements. Okay, fine. Now you take a list of n elements, you sort them, you get sorted list n log n. Okay, that's reasonable. What happens when you make it lazy? Now in laziness, things become incremental. Now it doesn't always work, but in the case of quicksort, it works. And the laziness, it means that the sorted list is generated bit by bit. Start from the first element. And it turns out the time complexity changes, okay? It's, instead of order n log n, it's n plus k log k. So what does that mean? So n is the size of the list, but k is how many elements we're asking. Maybe we only need the smallest element, and then k is equal to 1, okay? In that case, the time complexity will be order n. Maybe we only need the two smallest elements, the first two, and then it will be just a little bit more than n, okay? But maybe we need k elements, a small number of the small, maybe we need 5 smallest elements, so then it'll be n plus a little bit. So in general, it's n plus k log k. So you see, when k is equal to n, it goes back to n log n. But when k is small, it's much better than n log n, okay? In fact, it's really, really good and balanced. If I only need the first 3 smallest elements, it's basically linear time algorithm here, huh? N plus some constant. So it's a really good algorithm for finding the k smallest elements out of n. So we have made quicksort into this really nice generalization, okay? And there's it's even better than that. You don't need to know k in advance. If you want to write this in Java or something, maybe I want to compute the smallest 5 elements. I keep a small vector of 5 elements, I traverse, and I update that small vector, and at the end I have the smallest 5. Okay, fine. But what if I need the 6th one, the 6th smallest? I have to do it all over again because I don't have anything there. Well, this is not so dumb. This one is much smarter. If I ask for 5 elements, I get the 5. If I ask for the 6th one, it only does a little bit more work to get the 6th one because of the laziness. So you don't need to know k in advance. That's a really strong property, okay? You can run it and figure out how many you need at runtime when you see the elements. You don't have to pre-allocate data or whatever, okay? Okay, so that's what the algorithm does. I dare you to invent an algorithm from scratch that computes the k smallest elements out of n without knowing k in advance. Go ahead, write it. Try writing the code. I think you will see it's not so easy. But laziness does it for you. Okay? Okay, so let me now show you how it works. First, I will refresh your memory on Quicksort. Quicksort is a very straightforward kind of divide and conquer algorithm. Here I have a list L. I pick some random element out of L, any element. This one is called the pivot. Let's say X. And then I traverse L once, and I create 2 lists, L1 and L2. L1 has all the elements of L that are less than X, and L2 has all the elements of L that are greater than or equal to X. Okay, so I'm partitioning the 2 sublists. And on average, L1 and L2 will be about half the size. Not exactly, because it depends on these values. But if we have some kind of unordered list, it'll be typically half and half, around that. And then I do a recursive call to Quicksort. L1 gives me S1, which is a sorted list. And L2, which gives me another sorted list, S2. Now notice all the elements in S1 are less than all the elements in S2. That means in order to get the complete sorted list, I just have to concatenate them. I just have to do an append. And that's it. That's Quicksort. Okay? So that's a very nice, recursive, divide and conquer algorithm. Now there's other variations of that. Merge sort is another, it's a variation of this, okay? So this is Quicksort. And see, and how does it work? Okay, so here's an example of Quicksort. So if you do something like, let me write it down here, 7, 3, 2, I kind of chose them so it looks nice. 6, 4, 1, 9, that's my original list. I pick a pivot, let's say 7. So the elements less than 7, that makes 3, 2, 6, 4, 1, okay. The ones greater than or equal, that's 7, 8, 9. And here I would do it recursively the same. So if I pick 3 as the pivot, then the elements less than 3 will be 2, 1. The ones greater than or equal will be 3, 6, 4. And I go on. But let me just sort this. This gives me 1, 2. This gives me 3, 4, 6. If I append them, it gives me 1, 2, 3, 4, 6. And then if I append these two, it gives me 1, 2, 3, 4, 6, 7, 8, 9. Okay? So you see how it works, huh? It's very straightforward kind of divide and conquer. Now let me write the code for this. So here's a partition procedure. It takes a list L, it takes a pivot X, and it returns 2 outputs, L1 and L2. So it's just a case traversing L, and then it compares the element H with the pivot, and either it builds L1 or it builds L2. So you see how it's done, huh? L equals H bar M1. So M1 is unbound, huh? And then it calls recursively. So this is a tail recursive function, huh? Procedure, huh? You see it, we can do that because of the single assignment. And here's append and Quicksort. So the append is very straightforward. Quicksort, see how it works. So I will just take the first element of L as the pivot for naive reasons. It could be, it's better to take some random element, but I'll just take the first one for simplicity. Okay, and then I partition into L1, L2. I do the 2 recursive calls, and then I append. Okay, right? This is correct, huh? What do you think? So you can run this. Now, maybe I don't run it, just to save a little time. This algorithm is buggy. Okay, this is buggy, and I'm showing it to you because it's a typical kind of bug that you can get when you make recursive functions or procedures. So this one will not run. Looks nice, but it's buggy. In fact, it will go into infinite loop. Why will it go into an infinite loop? Have you remembered? Do you have experience? Remember your experience in debugging recursive functions? Well, you probably have already this kind of loops happening, right? So what could be the bug here? Does anyone have an idea? What's buggy here? Why? When you write a recursive algorithm, what you really have to be careful. There's something you have to really be careful about. So what is it? And this one is doing it wrong. Any idea? So that's buggy. If you run that, maybe it sometimes works, maybe it doesn't, who knows? But it will eventually go into an infinite loop. Why is that? It's actually very simple. But once I tell you, you should remember it always when you write recursive functions. So what do you think? What is the bug? It looks very nice, right? I'm following the rule here. And it looks, I showed it to you, it looks very nice. So what is wrong? What is wrong here? Any ideas? So I give you a hint, maybe. Whenever I do a recursive call, what do I have to be sure of that the recursive call, that it will terminate? What do I have to be sure of? There has to be, I have 2 recursive calls here. Quicksort L1, Quicksort L2. So Quicksort L will call Quicksort L1 and Quicksort L2. How can that go wrong? What does L1 have to be with respect to L? To be more precise, what is the connection between the size of L1 and the size of L? Yes?
So in this case, if the split isn't exactly at the middle every time, then maybe L1 will be bigger than L2 or the other way around.
Well, that's okay. L1 can be bigger than L2. But so L1 and L2, they will probably not be exactly the same size, huh? But it's not, the problem is not L1 and L2. The problem is L1 and L, the argument. So you're on the right track, but you have to go a little bit farther. You're getting there. You have to ask the same question between L1 and L. What has to be true between L1 and L for this thing to terminate? What must be true always between L1 and L? There is a property. What must be true, to make it more precise? What must be true between the size of L1, the length, and the length of L? That's pretty trivial. Now I am expecting answers, huh? I almost give it away now, huh? Come on, you guys, huh? When you write recursion, You have recursive case and you have base case. Now remember, eventually it goes to the base case. So here the base case, right? Nil, fine. Okay, more precise. What happens if L has exactly one element? What happens if L is a list of one element? What happens in this to this code? What is the length of L1? What is the length of L1? There's only two possibilities, huh? Come on, you guys. Or maybe we're way too early in the morning. I can understand that. I forgive you. Yes?
0. La taille de L1 sera la même taille que 0.
La taille de L1 sera 0.
Si L est une taille
Sûr? Toujours?
1. Je
Et
pense
si la taille de L1 est 0, quelle est la taille de L2?
que L1 sera également plus grand.
Ah, okay. So L1 can have a size 0, yes? But if L1 has size 0, I say it in English because of the video, then L2 must have a size 1. Right? Si L1 a taille 0, L2 doit avoir taille 1. Et qu'est-ce qui arrive alors? J'appelle la fonction avec une liste de taille 1 et il y a un appel récursif avec une liste de taille 1. Oh, oui.
Dans le append, L1 ne peut pas être une fonction, enfin une liste vide alors qu'elle sera vide quand on l'appelle.
L'append, les listes peuvent être vides pour append, c'est pas un problème. Hein? Oh, okay. So you guys are I'm sorry, but you're sleeping, okay? When I have a recursive call, I just give you the answer. When I call a function with the argument of size 1, and the recursive call also has size 1, what is that? That's an infinite loop. Because that one has size 1, and when it does its own recursive call, there will also be size 1, so it's going to go forever doing calls of size 1. It never gets smaller. You see that? That's an infinite loop. This program will go into infinite loop. How do you avoid that? There's a simple way to avoid it. All the recursive calls must have the size of the list be strictly smaller than the argument. That means L1 and L2 must be strictly shorter than L. Okay? You must guarantee that, and that property is not holding here, huh? Okay, so this is buggy, huh? Okay, you guys, you have to wake up, huh? Whenever you write a recursive function, you have to worry about that, huh? So this is buggy because the recursive call, when the list has size 1, one of them will also have size 1. And that means you have an infinite loop. Okay? Right? Ça va? Okay, super. Et donc, you can check that. I'm not going to check it. Here's the fix. The fix is to make sure that L1 is always smaller than L, and L2 is smaller than L. And how do I fix that? Actually, there's an easy fix. If I take the pivot, I can remove the pivot M. M will be strictly smaller than L. And that means L1 and L2, which will be strictly smaller than L, because I'm taking out this one element, okay? And I put it back in the append. So I do L, S1, followed by X, followed by S2. So the X goes in the middle, because it's the pivot. Everything less is on one side, everything greater than or equal is on the other side. So I just put it back here. So with this small change, I am guaranteed that the size of L1 and L2 are smaller than L, and therefore there's no infinite loop. Okay. Okay, let me run this thing. I have to run the Quicksort at least once. So here's a Quicksort. This is the lazy version, but I'm going to make it not lazy.
this. Why does it do all these control M's? That's not good. Okay. Well, I don't like these control M's. Why does it show all these control M's? Why did it work before? Oh. Is this going to work with these control M's? I'm not sure. It works. Okay, the control M's don't seem to bother things. Okay. Okay. I will make a normal append first. And a normal quicksort. Okay. This is not lazy yet, though. Okay. Okay, so here you see the answer, 2, 2, 3, 3, 4, 5, 5. Okay. So this is the quicksort. Okay. So you see that it works. I tested it on one example, so your short works, right? Okay. Now we make it lazy. But I will make it lazy after the break. So I will make small break now, and then I will show you the magic of lazy quicksort. Now, let me show you now lazy quicksort. First of all, we have 3 routines. We have quicksort, append, and partition. So we have to make them lazy. Quicksort and append is very easy. You just make them lazy with annotating the lazy. You get L quicksort, L append. But you have to be careful. Actually, partition should not be lazy, because you have to look at all the elements. You cannot find the smallest element out of L without looking at all of them. Okay? And also the partition has 2 results. So it's not clear which one. You actually need both of them. So actually making partition lazy is not a good idea. It's easier to keep partition eager. Okay? So that means we do the following. We take append and quicksort, and we just add lazy. So it's very easy to change the source code. And otherwise, it's all the same. We change the name up so that there's no confusion. L append and L quicksort. But partition stays the same. Okay. So let me run that. Okay. I'll have to start again with the doc container.
C'est quoi? C'est bon. Non, je mets comme ça et quand il y a des bouts de code, ben, je zoome dessus.
Okay, so here it is. We'll have to again put it in
façon, c'est
code.
parti.
Another one here. Okay, so here is partition lazy append, and lazy quicksort. Let me compile all that. Okay, oh, this is a partition. Okay, now we can do something like declare S in S is L quicksort. Like that. Browse S. Okay, so I'm running lazy quicksort. You see what happens here? You see that there's an S there. If I want some elements, I have to ask for them. S.2.1. That will ask for the second element, but actually will create the first two. So 1, 2. So the two smallest elements in my list are 1 and 2. So I've asked for the two smallest elements out of 9 elements. Right? If I go for S.2.2.2.1, I now have the 4 smallest elements out of 9. See, I have not executed everything. I've only executed a piece, a part of this. How much did I execute? We'll see. We'll think about it. We'll look at it. So you see how it works. I can now ask for as many elements I want. Okay. So you can run this. What is the time complexity of this? Before I do that, I want to show you a little bit more in detail how this thing is actually running. So I made a very detailed slide here, which shows you all of what's going on. And I would like you to follow this. So I made it in colors to make it easier. So the blue is the body of Quicksort, and the green is the body of Append. And I'm running Quicksort of 2, 3, 4, 1, and I do S.1. I want the first element. So S is needed, okay? And this S.1 is wait. S is needed. That means this lazy Quicksort will activate, and I execute the body here. So what does it do? It creates 3 lazy suspensions. You see that? On S1, on S2, and on S. And that's it. I execute the body. But S is still needed, and the S.1 is still waiting. That means the third one, this one, S equal Append, will activate because it's doing S. So I will execute the green, which is the body of the append. Now this one needs S1, which is the first argument. Now S1 has a suspension here. So that is active. So this blue code is this call up here that is activated. Okay, and it runs, and at the end I get S1 equal this thing. But I still don't know the value of S1. S1 is still needed. Once a variable is needed, it stays needed forever. Okay? So that means the Append will activate immediately. So this creates this lazy suspension. It's created, and it's immediately activated, because the wait needed is just going to go on. Okay? So again, I will execute the body here of a case of S1 prime is the first argument here. This one needs S1 prime. Now notice S1 prime is equal to L quicksort of nil. So that's a lazy suspension. So that one will wake up. But that's easy because now the argument is nil, the result is nil, and now we start doing bindings. S1 prime will now be bound to nil. Okay. But that is also the result of S1 here. S1 will be this case statement will execute. S1 prime is nil. So S1 is equal to 1 S2 prime. That's this green thing is executing, because S1 prime is nil. And now I know S1, and S1 is needed here, H bar T, it will be 1 followed by this L append. S will be equal to 1 followed by this L append. And now I bind S. And so the dot, S dot 1, it's been waiting since the beginning. It's only waiting. Okay, so this dot has been waiting nicely, very patiently, and all of a sudden it sees S is bound, and so it displays 1, and that's it. Okay? So you see, this looks complicated. It's actually not that complicated, okay? Okay, you have to be able to follow that. Here on the right, so on the left I'm actually showing the code, but on the right I'm only showing the lazy suspensions. Okay? So here, for example, S has a lazy suspension with a little arrow. S is needed, so these 3 lazy suspensions are created. S is still needed, so this third one is activated. It needs S1, so this causes this to activate, these 3 to execute. It's the body of L Quicksort, and so on. So here on the right, I'm showing the same thing as on the left, but only the lazy suspensions that are created and activated. I'm not showing the code. It's a little bit simpler. But to see really all what's going on, of course, you have to look at the code. Okay? So you see how it works, huh? I need something, I wait. Somebody else is activated, it works, and maybe it changes, more things get activated, and so on. Eventually, one of the bodies will bind the result, and the guy that's waiting will see the result eventually. Okay? Now, what is the complexity of this beast? We can compute it. I don't want to be too formal about this. What is the time complexity of lazy quicksort now? So here's a simple, let me do just a simple example. 3, 4, 1. I partition, I get 2 lists here, on the left and on the right. But if I'm only looking at the first element, these will create more quicksort calls, but this one will not, the second quicksort call will not be activated. So I'm actually only executing things on the left, okay? So here I have to traverse the whole list, n. Here I traverse n over 2, but if you keep going, it'll always be the left one. Right? If I make a more complete picture, I have a partition, I have a list here, I partition it, which creates 2 lists, but since I only activate the leftmost L quicksort, I will partition this one. Again, I will only activate the leftmost one. It's because I'm looking for the first element, and so on, until I have 1 element. So it's I traverse n over 2, n over 4, and so on, until I go down to 1. So the total amount of work done here is n plus n over 2 plus n over 4, etc. If you make this sum, you'll see it's just 2n. It's proportional to n. So the partition calls for making the smallest elements is n, and that's it. If I want the k smallest elements, I don't just want 1, but I want a bunch of them, then it's like I'm running a small quicksort. Maybe in this piece, I'm running full quicksort here. So this part is running completely because I want all k elements here. But this is only a size k thing. It's like a mini quicksort. When I get down to the small list of k elements, and I need all k, then that thing will be executed completely. Okay? That means this, and this takes n log n. This is a full quicksort, but only on k elements. A full quicksort, mini quicksort, as soon as the partition list has at least k elements. So it'll be a little bit more than k, maybe. But we can just say it's around k. So the extra time complexity is k log k.
So if you make the sum of those two, it's n plus k log k. Okay? That gives me the time complexity of the whole beast. That's pretty smart. That's pretty good, actually. For calculating, it actually creates a smaller quicksort, and then it executes it completely. That's actually a pretty smart way of solving the smallest k out of n elements. Okay. Okay, so that's quicksort. So this is an example of the magic of laziness. Laziness has really made a smart incremental algorithm here. Okay? It's efficient in time, in space, has a good complexity. What more can you ask? And it's easy to write. It's the same source code as the full one. Okay? So laziness cannot always make things incremental, but if you know that, you can kind of write your code so that it's incrementable, so that it can be made incremental. You have to kind of write it in an incremental way, and then the laziness will do all the dirty work for you, okay? And this is not just a toy, this is a real practical approach, which we will see more of next week when we go into advanced declarative algorithms, okay? Okay, so that's all I'm going to say about laziness. Let me now step back and try to talk a little bit more about declarative programming. So this is a main theme of the course, In fact, programming is divided into two parts, declarative and non-declarative. You always want to do declarative, normally, except when you interact with the real world. That introduces non-determinism, so that forces you to be a little bit non-declarative. So that is generally how programming should be done. Now, the question there is, what exactly is declarative programming? And I want to answer that question now. So we're going to be very precise and a little bit formal. Okay, so we have seen 5 declarative paradigms. Okay? Sequential functional programming with values. This is like in a language like Scheme. Sequential functional with single assignment. This is nice because list functions are tail recursive. We've seen deterministic data flow, so concurrency. We've seen lazy evaluation and laziness. And we combine them to have lazy deterministic data flow. So those are all declarative paradigms. But what does that mean? Okay, what does that mean that they're declarative? Well, I want to answer that question. I want to tell you, really, we want to go into that. And we start from functional programming. Functional programming, which is the core, and we saw a little bit of that in the previous course. We saw the lambda calculus. But I won't go too much into the lambda calculus now, but I will refresh your memory on one thing, which is the Church-Rosser theorem. This is the main theoretical result for lambda calculus. This is the reason why functional programming is the core. Okay? Why is this theorem true, actually? That's a really good question. And there's lots of answers to that, but I won't go into that. So it says the following. If I start from some expression, EA, on the top left, I do reduction steps. So this is lambda calculus. So lambda calculus is a formal model of functional programming. We saw it in the previous course, and we actually did exercise in it and so on. And this is what theoreticians, mathematicians study when they study programming. They start from the lambda calculus. Okay? So there's many variations of lambda calculus, but I don't want to go into all that. I just want to show you one main thing. So all functional programs can be encoded as lambda expressions. And these expressions are reduced step by step. Okay? So each little arrow here is a single step. And if you want to know more, you can go look at the lectures of the previous course. But if you have started with some program, EA, some expression, and you reduce it, until you get EB, okay? So this takes 0 or more steps. But you can also choose different reductions. In fact, in a big expression, you can reduce it in many ways, okay? You can say, I want to start here or here. So if you reduce it in another way, and this one I'm going to write down, going down here, to E2 prime, E3 prime, ending up to EC. So now I have these two different expressions, EB and EC. The theorem says there exists a term ED such that EB can reduce down to ED, but EC can also reduce down to ED. That means the two reductions come back together again. What it means, basically, is that the reduction order doesn't matter. That eventually you will always get the same result. And this is a major property. We say it's called confluence. The lambda calculus is confluent. And this is the reason why declarative programs are so nice, and why there's no non-determinism, okay? It's also called the Church-Rosser property, okay? That's another way to say it. So this is lambda calculus. Now the question is, how does this go to all these other neat paradigms that we did, deterministic data flow, and so on? So what happens there? So we see that pure functional lambda programs are nice, confluent. It's a nice property, and it's very strong, and the whole edifice is built on it. But we did more than that. We added concurrency. We added streams. Streams are interesting because they keep growing. That means the program never actually terminates. We give it some elements, it does something. We give it some more elements, it keeps going. It's never actually really terminating. So what does that mean, really, in terms of declarativeness? We also have single assigned variables. So variables can be unbound. Well, the lambda calculus doesn't have that. The lambda calculus has only values. It doesn't have unbound variables. So what happens with these funny unbound variables? So how does the confluence, the Church-Rosser thing, change when we have all this extra stuff? Okay, so that's what I want to answer. And I want to explain three things. First of all, concurrency is easy to handle. So the first one here, concurrency is easy, because concurrency is already part of the Church-Rosser. If I have a big expression EA, and this expression contains multiple agents, and I execute all of them kind of concurrently, that's okay. It means I'm choosing the reductions according to some scheduler, okay? But Church-Rosser says it doesn't matter. They will all get the same result. So the concurrency already doesn't make any problems. So the problems is the two other things, the streams and the single assignment variables, okay? So let me look at these two. And I introduce two concepts. One is partial termination, where the program never really completely stops. It only stops temporarily, but it can start going again and then stop temporarily again, okay? When I have a stream, I can give stream elements and I do a computation, but then I can make the stream grow and it does a little bit more. So that gives me a more general notion than just stopping. It's partial. And finally, what happens if there's unbound variables? Well, that actually, the store turns into something that comes from logic. The store represents a logical formula, and this gives us equivalence store. So this I will explain also. Okay, so let me start by partial termination. That's the easiest thing to explain. So let's say on the top left we have a concurrent agent, like we saw, times H2. Okay? It has an input stream and an output stream. And maybe it's multiplying by 2. So if the input stream is 1 underscore, the output will be 2 underscore. Fine. If I extend the input stream, 1, 2, the output will be 2, 4. And I can keep extending it. So how is this functional? Because the program never terminates. It never really terminates. It's actually, there's no end. The stream can keep growing forever. So there's really no termination. But actually, if we look at it in the right way, we can say there is kind of termination. Okay? So assume that we give some S1, and we don't change it. And 1, 2. And we stay 1, 2. And we let the program run with a fixed S1. Then it will terminate. And S2 will reach a final value, which is 2, 4. Okay. This is partial termination, because it's not completely terminated, but it's temporarily terminated. So 1, 2 has given 2, 4. Okay. There's also a theoretical, in some theory papers, it's called a resting point. You can see the program kind of rests. When 1, 2 is given and you stop, the program runs and then it stops. But it's only temporary. It's only resting. It's not actually done. It's just resting. Okay. If you keep binding S1, it will start up again. But each time the S1 is fixed, it will eventually stop. Okay. So that's partial termination. So we only have to worry about partial termination for streams, about functions. We don't have to worry about the full termination. Okay, so that's one thing. So that's one way to handle it. But now the more important thing is what happens when there's unbound variables in memory and they stay there. Well, actually, the stores are not containing values anymore. They're containing logical formulas. So this is actually first order logic. So I don't know if any of you have seen a course on first order logic. Any of you have seen first order logic? Who has seen first order logic? Nobody. None of it? You have not seen the course on calculabilité? No? Okay, that shows a little bit. I used to give a course on first order logic. Unfortunately, unless you're doing mathematics, you won't see so much first order logic. But it's not a problem. I'm not assuming first order logic. I will explain exactly what you need to know. So this will actually give you a little piece of logic. What I'm going to explain now is a little piece of first order logic. First order logic is a very big part of mathematics. And you can formalize mathematics, you can write systems using logic. Okay, so logic is a very big thing. But I'm only going to show you a small piece of it, which we need for showing equivalence stores. Okay, let me start with an example. Okay, I claim that a functional programming with single assignment variables is still functional, but instead of the results being equal, they're actually, the stores are not equal, but they're equivalent. So let's see how to make it precise. So here's a little program, here's a little program with 3 threads. And it does x1 equals foo zw. Foo is just a record with 2 arguments. Y equals foo zw, and z and w are just unbound variables. And then it does x equal y. So I have 3 threads. Now, depending how you execute this, we can get different bindings in the store. If we start by executing T1 and T2, then we will bind X equals this foo thing. So this is the store sigma. And it's a set of bindings, variable equals something. X equal this foo thing, and Y equal also foo. And then X equal Y will verify that X is equal, and it's done. So if T1 and T2 execute first, sigma looks like that. But we're not guaranteed. The scheduler might think differently. The scheduler might say, let's do T1 and T3 first, and T2 after. So if we do T1, we get this, x equals foo ZW. If we do T3, it's x equal y. So this is binding y, since x is already bound, y equal x. And then the final one, T2, will just verify that it's the same. So this gives me another store, sigma prime. So we have two stores, sigma and sigma prime, which are different. They're not the same, huh? But somehow they represent the same thing. You can kind of see that, huh? Both x and y are going to be records foo ZW. But the bindings are actually different. But it doesn't really matter that they're different because the values that these stores represent are the same actually. So how can we make that kind of precise? You can see the intuition, huh? Sigma and sigma prime are different. They're actually different. But in some sense they're the same because they kind of represent the same thing. So that's very vague, huh? So we want to be kind of very precise. How do we make that precise? How can we express that sigma and sigma prime are the same? Okay. So here's one approach. And this is going towards logic. So assume we have now these two stores, sigma and sigma prime. The bindings of x and y are different in sigma and sigma prime. Now they're different. But the possible values of x and y are the same. Both x and y will be records with a label foo and with two arguments that can be any value, z and w. Okay, both of those. So how do we make that precise? Well, one way is the following. A store, so any store, sigma, somehow corresponds to a relationship, a connection between the values. The store sigma is telling us, so this sigma, is telling us that x is a record with label foo and argument c and w, and that y is a record with label foo and argument c and w. That's what it's telling us. But if I give any possible values of x, y, z, and w, either they could be in a store sigma or they are not. So if they are of this form, then they could be in a sigma. But if they're different, if x is not a record, then it cannot be in a store sigma. Okay. So somehow the store is telling us that for some x, y, z, w, it's true. There could be in there. Or for other ones, it's not true, so it's false. Okay? So the store sigma is kind of a thing that can be true or false. If I take any x, y, z, w and put it in there, then either this could be true if the x is a record and y is a record and so on, or if it's not a record, then it's false. So the store sigma is kind of dividing the world into two parts. The values that are true and the values that are false. Okay? Which means that it's a logical formula. So a logical formula is an expression that can be true or false. So we write it in a little bit different way. So let's, instead of writing it like a set, let me write it like this, where I have these two equalities, and I put this symbol here, which means and. So I write it like a logical expression. So this is kind of inspired from logic. So this thing, for any values of x, y, z, w, this can be true or false, right? If I pick them right, it's true. If I pick them wrong, it's false. So it represents a set of values, and all the ones for which it's true. You see that? Every store is kind of a logical formula. Okay, so that's one thing. Now, we are picking values, x, y, z, w. The operation of picking values Let me give it a name. Let me call that an interpretation. When I take a store, all the symbols in sigma, I will assign values to them. X is this, Y is this, Z is this, W is this, okay? And also the record symbol, the foo, I will assign a function to that. A function of 2 arguments. Okay? And an interpretation can be either true or false. So if I do x equal f x1 xn, it's true if the value returned by the function is equal to the value I've assigned to x. So if I pick values that make it true, it's true. If I pick different values, it's false. Okay? And if I take a store, which is a combination of those, it's true if all the bindings are true. Otherwise, it's false. So you see, if I interpret the store, I'm actually giving values to the variables. And with those values, the store could be true or false. It's kind of representing a logical formula. See that? How stores can represent some kind of logical formula. Okay, and now one more thing. I talk about a model. So that an interpretation is any old values. I assign any values. But a model is only when it's true. So a model is kind of a good interpretation. One that's kind of doing the right thing so that the store is true. So the store the model is kind of the thing that the store is representing, okay? As an interpretation where I've picked all the values so that it's true, okay? And that's it. That's all I need to do. Now I'm done, actually. Okay? Now we can define when 2 stores are equivalent. So each store represents a logical formula that can be true or false. 2 stores are equivalent when, no matter how we assign it, so for any interpretation, they're either both true or both false, which means they're kind of the same. We cannot find values such that one store is true and the other one is false. That means they would be different. Okay? That's the thing. So no matter how we pick the values, both of them will be either true or they will both be false. So they're actually the same. Okay? And if you look at the previous example here, the one on the top here, you can see that's right. If I pick any values for x, y, z, w, sigma will be true or false, depending on whether x is actually, I've picked a record, okay, for x, and so on. But sigma and sigma prime will both be true at the same time, with the same values, or they're both false. I cannot make them look different. They're actually representing the same information, in a sense. And I make a notation for that. So that's it, that's the idea. And I introduce a nice notation. So this one coming from logic, which is this bar with the 2 stripes there. This is a notation coming from logic. So let me make a picture here. So it's like this notation. So alpha is a logical formula, beta is logical formula. So what this means is that beta is true in all the models of alpha. That means I take an interpretation that makes alpha true. Beta is also true there. That's what I'm saying. So that's what this means. Okay? Beta is true in all models of alpha. So 2 stores are logically equivalent if sigma prime is true in all the models of sigma, and sigma is true in all the models of sigma prime. So if one of them is true, the other one is true. If one of them is false, the other one will be false. So they're equivalent. They're both true at the same time, or if they're not, then they're both false at the same time. You can also write it slightly differently here using this equivalence operator. So this little double-headed arrow, it means that either both sides are true or they're both false. And if I write this with no model, no formula here, It's talking about all models, all possible interpretations, all possible assignments, values. This is true. That means if sigma is false, then sigma prime is false. If sigma is true, then sigma prime is true. They're equivalent. It's also called, this is called a tautology. Okay, this is a tautology. That means it's true in all models. That's coming from logic, huh? So I'm actually introducing a little bit logic here, huh? Okay? So two stores are equivalent if no matter how you assign the values to the variables, if one of them is true, the other one is also true. And if one of them is false, the other one is also false. That's it. Okay? So that is it. That way we can see whether the stores are the same. Okay? So these two stores up on the top here, they're the same. They're saying the same thing, actually. They have the same information, according to this definition. Okay? So what I've done now, in the last 10 minutes, is I've essentially given you an introduction to first order logic. Okay, now this is not a course in logic, but first order logic is actually a very important thing. Most of mathematics can be built on top of first order logic. So I'm not going to explain all of first order logic. I only showed you a piece of it. I showed you a logical formula. This is an expression. It expresses a relationship between values. And then I showed you a model. This is a set of values that makes these formulas either true or false. So the model is like the semantics of the logic formula. The logic formula is just an expression, some kind of a grammar thing, syntax. But the model tells me whether it's true or false. That expression, so it's kind of doing the semantics. So the two stores are equivalent if they have the same models, actually. And that's it. I'm not going to tell you more about logic. Okay? That's all you need to know about logic for this course. You need to know the notion of a logical formula and the notion of a model, the way I explained it here. Okay? Okay. If you want to understand first order logic more, actually that's a good thing. First order logic is a really interesting thing, and many, many, many things are based on logic. And you all getting bits and pieces of it in their courses. There used to be a full course on logic, which was given by me, okay? But unfortunately, when the curriculum was reorganized, the course disappeared, and logic, a small piece of logic is given in the course of calculability from Yves de Ville, but that's only a little bit of logic. So there used to be a full course on logic, which was really nice, but unfortunately it doesn't exist anymore. So I give you just a little piece of logic here. Now, actually, there are programming languages completely based on logic. And the most famous one is called Prolog, Programming in Logic. Prolog is interesting because this year, 2022, is the 50th anniversary of Prolog. So there's like a celebration. The Prolog, there's still many Prolog implementations. Okay, you can download them that are free and they work very nicely. Prolog is 50 years old now. It's pretty amazing and still being used. Okay, people still using Prolog. Language based on first order logic. So that's an old thing, actually. There's also constraint programming, which is based on first order logic. And this is interesting because we have in our department experts on that, especially Yves de Ville and Pierre Chausse. They are world experts on constraint programming, and there are programming systems based on this. So if you're interested in seeing the power, it's very powerful actually, you should take the courses on constraint programming, okay? And a final thing, everybody uses logic because database query language, SQL, SQL, the SQL, which is used everywhere, is also actually logic. It is also first order logic, okay? It is a logic language. So Java with SQL is actually a combination of object-oriented and logic, okay? So logic is used a lot here. So I've just given you a small piece of logic, yeah? Just enough so that we can define declarative programming. So this, what I'm showing you here, it's actually useful to really try to understand it, because if you ever learn logic later, you will continue this, okay? This is giving you the kind of the beginning of first order logic, okay? We need it here for defining equivalence between stores, but in fact, it's much more useful than that. Okay, so now we know enough to define declarative programming, and now the definition is actually very simple. It's in the record. We can say precisely what it means. So if I give you a program, the program is declarative if for all possible inputs, then all executions for those inputs will either not terminate, so they all go into infinite loops, or all of them, all the executions reach partial termination, and they give logical equivalent stores. That means if I run the program, and all executions means all choices of the scheduler, the current program, so no matter what the scheduler does, they will all give the same results. But the same means logically equivalent. It doesn't mean exactly the same bindings. It means logically it's the same. Semantics, okay? And they all reach partial termination. So when I say there is no observable non-determinism, what I mean is that it's doing this. Okay, so this is an important definition for declarative programming. And all 5 paradigms we saw are all declarative according to this. Okay? Okay, so that's what I wanted to reach. So you see, it's important. Logical equivalence is an important thing. Okay, now there's just a few small things. Failure confinement. So, okay, so declarativeness, as you gather by now, I consider it very powerful and important. So we want to write applications as declarative as possible. So that's a major theme of the course, of course. But there's another thing. What if there's a bug that causes the program to become non-declarative? How do we fix an application because it's buggy, it becomes non-deterministic. It becomes non-declarative. Okay? So it gives you some kind of non-declarative behavior. So there's actually 2 ways of getting non-declarative behavior. There's a good way and a bad way. The good way is that the program interacts with the real world, and we see that later. That kind of non-determinism is unavoidable. But now, let's see what happens if you have a bug, and the bug makes it non-declarative. The idea is to kind of fix it so the bug does not propagate. Okay? Okay, so there's an important fact. Okay, so it is a truth, universally acknowledged, that a program of a certain size must have bugs. Okay, all big programs have bugs. If you have read Jane Austen, then I apologize, because this phrase is coming from a novel by Jane Austen. Do you know Jane Austen? Any of you? Pride and Prejudice? Orgueil et Préjugés? No? You don't know it? It's a great book. Well, this sentence is actually inspired by Jane Austen. Okay. But it's true. So here's a program. X is 1, Y is 2, X is Y. Notice it doesn't work. It's inconsistent. Okay? So this is, let's say you have a huge program, but at the end of the day, it's doing this. So that's a bug. Okay? this will always raise an exception. And depending on the scheduler, there are 3 possible stores that are different. It's either 1-2, or 1-1, or 2-2. Which one do we get? We don't know. Depends on the scheduler. This is an observable non-determinism. That's non-declarative, and it's because of the bug. So we can do failure containment. We hide it so that the program becomes declarative again. We kind of put a box around it. So here's the way to do it. So I have my program, 3 things here. I put a try-catch. I catch the exceptions. And if there's any error, S1 or S2 or S3, then I say that xy is equal to 1. It's like a default. So I'm hiding the non-determinism. But if there's no error, then I pass up x1 and y1. Okay? So I'm actually, if there's an error, I hide it. I make the program deterministic again. That's something you sometimes have to do. That's the real world for you, okay? And this is called failure confinement. Okay, let me just make one more thing and then we're done for today. So here is a chart giving all possible declarative paradigms. And we've seen it. So functional programming with values, functional programming with data flow variables, deterministic data flow is here, lazy deterministic data flow is here, lazy evaluation is here. Here we have lazy evaluation with single assignment variables. These are 6 paradigms. Some of them have languages attached. So this one, there's a language called Scheme. This one, it's Prolog, or deterministic subset of Prolog. This one, it's Haskell. These 3, there's really not so many languages, or none, to do it today. But it will be done in the future. Okay? So this is kind of a future-oriented. Okay? You will, in the future, see many more declarative paradigms appear. Okay? Okay, let me summarize what we saw today. First, we saw lazy evaluation. Okay? And I showed infinite lists. I showed lazy quicksort, Hammock, what you can do. Second, I explained what is declarative programming using confluence, partial termination, and logical equivalence. So I actually gave you an introduction to first-order logic. And next week, we're going to show advanced algorithm design. I'm going to show you how to make really efficient, smart declarative algorithms, basically using laziness as a very powerful technique for algorithm design. So I will go with